Hey guys, welcome back. This is the second section of Chapter 5, titled Molecules and Compounds. Again, this is lecture part 2 of 2, Chapter 5. Okay, we left off, we talked about ionic compounds. Alright, now we're going to talk about covalent. And just a reminder, covalent compounds are a result of the covalent bond that's formed between two non-metals that share electrons to complete their valence shell. So again, when two nonmetals form a compound, both nonmetals need electrons to complete their octet. Since neither wants to give up, no ions are formed. Instead, they share electrons, and we call these covalent or molecular compounds. So this is just a really quick example of a hydrogen molecule. When we say hydrogen molecule, remember that's a diatomic, right? So H2. And before bonding, a hydrogen atom has one electron, and when they come together, each hydrogen atom needs two electrons. So when they come together, they just share, and then you have this covalent bond that is formed, which is a covalent bond is the sharing of two electrons. Okay, so one bond equals two electrons shared. So the hydrogen on the left has two electrons, and the hydrogen on the right has two electrons. So they're both happy. So this is different than ionic compounds. Remember, ionic compounds are formed through ionic bonds. And an ionic bond is the electrostatic interaction between positive and negative ions, a metal to a nonmetal specifically, and metals form cations and nonmetals form anions. Again, covalent bonds, the sharing of electrons. Again, this is a nonmetal to a nonmetal. An example of this would be ammonia, NH3. Okay, because remember, and this should kind of make sense to you guys if you look at the periodic table, nitrogen likes to form a -3 anion when it binds to a metal. Okay, that means that it needs 3 electrons to form a full octet. And turns out in the valence shell of nitrogen, it has 1, 2, 3, 4, 5 electrons. So that's 3 short of 8. So that is why when it binds to hydrogen, it binds to 3 hydrogens. Okay, so hydrogen will share its 3 electrons, giving nitrogen 8, and nitrogen will share one of its electrons to hydrogen, giving each hydrogen atom 2 electrons. So everybody's happy. So again, left side of the screen or left side of the periodic table are metals, right side are nonmetals. So just to make sure we understand the difference between ionic and covalent compounds, let's look at a list here. Sodium chloride, NaCl, again that's a metal plus a nonmetal, so it's ionic. CO, 2 nonmetals, so covalent. NH3, 2 nonmetals, or a metal and a nonmetal, covalent. Magnesium oxide, we have a metal and a nonmetal, so that is ionic. And then this is carbon tetrachloride, which we will learn in this lecture how to name. Carbon tetrachloride, carbon is a nonmetal and chlorine is a metal, or a nonmetal, excuse me, so nonmetal, nonmetal, covalent. So naming simple covalent compounds, this is how you're going to do it. Case 1. So there are 2 cases. The first case is there is 1 atom of the first nonmetal, like this, CO2. Okay, there's 1 of the first nonmetal. So you're just going to name the first nonmetal carbon. You're going to use a prefix to indicate the number of atoms of the second metal. Since there are 2 oxygen atoms, you're going to say dioxygen, right? And then you're going to change the ID or the ending to IDE, so it's going to be dioxide, and then you're going to put it all together. Yay! Carbon dioxide. So these are the prefixes that you're going to have to kind of commit to memory. 1 mono, 2 di, 3 tri, tetra, penta, hexa, hepta, octa, nona, and deca. Okay, most of these are pretty intuitive. You already know that, all right? The only problem is people get kind of tripped up with the penta and hexa and hepta. Everybody knows octa. Deca is pretty straightforward. Decade. Tri is always 3. Di is always 2. Don't get 3 and 4 confused, and don't make sure you have 5, 6, and 7 down. So penta, 5. Hexa, you can think hexagon, right? And then hepta, 7. So the second case is there's more than one atom of the first nonmetal, all right? So like this guy, P2S5. So use a prefix of the number of atoms of the first nonmetal. So since there's 2 phosphorus, you call it diphosphorus. Same thing with the second nonmetal, and again we're going to change the ending of the second nonmetal to IDE. There's 5 sulfurs, so it's going to be pentasulfide. Penta meaning 5, sulfide, right? We're changing, it should be sulfur, or is sulfur, but we're changing the ending to IDE. So put it all together. Pretty. Diphosphorus pentasulfide. So let's try these. I have some covalent mixed up in here to make sure that you guys are still remembering all that. So first one, sodium iodide. This is a covalent compound. All right, next one, FeCl3. If you remember, iron is a variable charged metal. Okay, so when we write this out, we're going to have to use Roman numerals to indicate the charge on iron. We don't know the charge on iron. We have to look at the anion. There are 3 chloride anions. Each chloride anion is worth a -1, right? A -1 charge. And we know that. We've attacked it from several different angles, but essentially we look, it's group 7 on the periodic table. That means it has 7 valence electrons. That means it only needs 1 electron to get to a full valence shell. So that is why it is always a -1 in ionic compounds. And there are 3 of them. So that means the overall anionic charge is -3. So if it's -3 on the anions and the whole compound is charge neutral, or the whole formula unit, we should say, is charge neutral, then iron has to be iron 3. So you're going to write iron, Roman numeral 3 to indicate the charge on iron. It's because it's a variable charged metal. All right, we don't do this with metals that are fixed charges. And then chloride. Okay, CBr4. 2 nonmetals, carbon and bromine. This is case 1 because there is only 1 carbon. So you're going to say carbon tetrabromide. Al2O3, again, aluminum is not a variable charged metal, so we don't have to include parentheses. So it's just aluminum oxide. N2O5, that is a second example of a covalent compound because there's more, or the second case, I should say. There's 2 nitrogens and 5 oxygens, so you just need to remember di for 2 and penta for 5. And remember that we place oxide, or oxygen, we call it oxide, so dinitrogen pentaoxide. BAF2, this is an ionic compound, barium is a metal, fluorine is a nonmetal. Because barium is not, it is in the second column of the periodic table. It's not a variable charged metal, so we don't need to include Roman numerals. It's called barium fluoride. SNO. Okay, so first of all, what is SN? That is 10, all right? So that's something that you're going to have to know. Just by this point in time, you should just really become familiar with things on the periodic table. Most of the time, we don't really go past N equals 6, right? We maybe deal with a little bit of francium and radium. We don't really talk about the lanthanides and actinides a lot, so we're just looking at 55, 56, and then 57 essentially through 86. I'm not asking you to memorize, but just kind of become familiar, all right, with where everything is. How iron is of Fe, that is something you need to know, but 10 is Sn. This is a this is a ionic compound. 10 is a variable charged metal. It is not in the first or second column. But what is the charge on 10? Well, right away you should be able to tell, because oxygen is a -2 when it's in ionic compounds. So 10 has to be a +2. So we're going to call it 10,2 oxide, and we indicate again the charge on 10 with the Roman number 2. And then finally, PF5, this is case 1 for our covalent compounds. That's going to be phosphorus pentafluoride. Okay. So now we're going from from the name to the formula. Okay. So sulfur hexafluoride. Hexa meaning 6, and then fluor, so it's sulfur hexafluoride. Magnesium sulfide. Magnesium, this is an ionic compound. So when we're looking at ionic compounds, we have to think about charge. Magnesium is a +2 because it's in the second column. Sulfur is always a -2, so it's just MgS. Magnesium oxide. Oxygen is above sulfur, same column, so it's going to be same charge. Oh, I'm sorry, I was thinking oxide. Magnesium iodide. Magnesium is always a +2. It's a fixed charge. Iodide is also a fixed charge. It is always a -1. So we need 2 of them to cancel out the +2 charge on magnesium. So it's going to be Mgi2. Silver 1 oxide. Silver is a variable charged metal. But what you need to know specifically is that what that Roman numeral 1 means. It means that silver has a +1 charge. Since we already know oxygen is always a 2-, then we're going to need 2 silvers for every 1 oxygen. Nitrogen dioxide, 1 nitrogen, 2 oxygens, covalent compound. And then we have lead 4 chloride. All right, so the charge on lead is +2. The charge on a chloride anion is -1, so we're going to need 4 of them. So we have lead Cl subscript 4. Just a heads up too, there's always a systematic way of naming things. What we've been using is the IUPAC way of naming, International Union of Pure and Applied Chemistry. But some compounds are still named with their old common names. Some examples of this would be water, which you already know, ammonia, NH3. We don't call it nitrogen trihydride, we call it ammonia. And then just another example, nitrous oxide, N2O. Water and ammonia is something that you're going to have to be familiar with throughout the scope of this, throughout this course. Okay, so we are switching back to ionic compounds right now. Okay, switching back to ionic compounds, and I want to introduce to you a new type of ion. Before we were looking at just single atom ions, magnesium +2, fluoride -1. But in chemistry, a group of atoms can also collectively have a charge. Okay, there are lots of reasons for this, and when you go into organic chemistry, you'll probably draw the structures of these guys, but they are non-metals, right? Chemically, or we'll say covalently bound together with a charge. I also realize here that I have it's supposed to be polyatomic, so sorry about that. These are called polyatomic ions. Polyatomic. They are a group of non-metals that are covalently bound together and have an overall charge associated with it, okay? And the reason why that is they basically are really stable with these minus charges, all right? You'll notice that there's only one polyatomic cation, that's ammonium, NH4+. Everything else has a charge on it that's negative, okay? So people have a hard time with the polyatomics just because they hate memorizing, and this is just all what it boils down to. You are going to need to memorize these, all right? You're going to need to memorize the actual formula, and you're going to have to memorize the charge. But I can make it a little bit simpler for you by telling you which ones you're going to need to memorize and a good way to commit them to memory. The best way to commit them to memory is to make note cards. That's for sure. Okay, but I'll just take you through this really fast. So it's possible for a group of atoms to carry a charge. All right, this is everything that I've already talked about. The whole group carries a plus or a minus charge. I've only exposed you to one cation, that's ammonia, NH4, okay? And everything else has a minus charge. These are just some of them, but these are all called the polyatomics, okay? These are just some of them. There's a whole other slide of them. So just become familiar with the names. Hydroxide, cyanide, right? All -1. You have nitrate and nitrite, all -1. The only difference between nitrate and nitrite is an oxygen atom. And then the ones on the right, these are all chlorine and oxygen. Okay, so perchlorate, chlorate, chlorite, hypochlorite. All right, those all have the same charge, a -1. Underneath, you have acetate. All right, so the nitrates and nitrites are a group, and the chlorates are also a group as well. All right, we also have the sulfate and sulfite, carbonate, phosphate, chromate, dichromate, bisulfate, bicarbonate, and permanganate. Permanganate's the only one with a metal associated with it too. If you'll notice, it has manganese on there within it. The sulfates and sulfites always a -2. Carbonate -2. Phosphate is a -3. Chromate and dichromate are -2. All right, and everything on the right is all a -1. So these are the ones that you're going to have to memorize, the ones that I have in red. Okay. And like I said, note cards are the best thing, but there's also a really, I want to say it's a more simple, but it's a more simple way of helping. There are simple aids for you to memorize this, besides just note cards. Let me go back to that really fast. We will talk about that in just a second, but let's first talk about how to name, right, with the polyatomics. Many polyatomic ions are oxy anions, which means they're an anion containing oxygen. And you can see this, basically all of these have oxygen, right? The only thing that doesn't is cyanide, and I'm not seeing anything else. They basically all have oxygen except for cyanide. When a series of oxy anions contain different number of oxygen atoms, there's a systematic name for that, according to the number of oxygen atoms in an ion. If there are 2 ions in this series, the one with more oxygen atoms is ended in ATE, the one with fewer is ITE. So the one with more oxygen atoms is ATE, the one with fewer is ITE. So let's go back. Oh, I don't have to go back. So nitrate and sulfate. Ni for the nitrogen atoms. ATE, right, this means that, first of all, the charge is the same, so you don't have to memorize the different charges. They each have nitrogen. The only thing that they differ from is the number of oxygens. The one nitrate has 3 oxygens, nitrite has 2. Okay, if we go over to the sulfate and sulfite, same thing, right? SUL, that's for the sulfur, and ATE, this time it has 4 oxygens, all right, with a 2- charge. And then the sulfite, ITE, has 3. So if there are more than 2 ions in a series, okay, back here, oops, excuse me. Nope, I lost my spot. Okay, there we go. So the sulfates, so sulfur, oxyanions and nitrate oxyanions both are of a group of 2, okay? There are groups that have more than 2. So, if there are groups that have more than 2 ions, then we're going to use prefixes hypo meaning less than and per meaning more than. All right. So, let's start over in the far left. We have the chloride anions, oxyanions, okay? We have 4 of them, all right? We know that Cl, they all have the same charge. And then if you look in the middle group, these are just the bromine oxyanions. They all have the same charge. And then all the way to the far right, we have the iodide oxyanions. Still all the same charge. And they're also in order, each one of them, they're in order of 1 oxygen, 2, 3, and 4. So if we start off with each one, if you look at it, each one with 2 oxygens. We've got chlorite, bromite, and iodite. 2 oxygens, they all end in ITE. We bump up 1 more oxygen to 3. We have chlorate, bromate, and iodate. That's with 1 more oxygen. Now, with another oxygen, okay, since we already added the ATE, now we can add the per at the beginning, at the prefix. Per meaning more than. So per chlorate is 4 oxygens, per bromate is 4 oxygens, and periodate is 4 oxygens. We can also add, instead of per, we can add the prefix hypo. That's going to mean 1 less oxygen. So if the ending is ITE, we already know that ITE means 2 oxygens, right? Chlorite, bromite, and iodite have 2 oxygens. If we throw a hypo in front of it, then that's saying less than. So less than 2 is 1. So hypochlorite is 1 oxygen, hypobromite is 1 oxygen, and hypoiodite is 1 oxygen. So if you understand this, there's no memorization. If you remember, if you understand, this slide, there's no memorization except for the charges. And if you understand this slide, there's no memorization except for the charges, which all of these guys are the same. So hopefully that makes everything a little bit easier. So let's talk about naming ionic compounds, or naming ionic compounds containing polyatomic ions. Again, polyatomic ions, they're ions, right? So there are a compound made up of non-metal elements chemically bound together that possess a charge. So since they possess a charge, most of them with the exception of one has a negative charge, they can be used instead of single atomic ions in ionic compounds. For example, we have KNO3. So what you want to do with KNO3 when you start to analyze it, you should know, after a little bit of studying, you should be able to recognize that NO3 is a polyatomic anion. The only way that you would know that is that you're hearing me tell you this, and then you're just remembering that NO3 is a polyatomic anion with a charge of -1. All right? There's nothing necessarily intuitive by looking at that KNO3 and saying, oh, well, clearly it's this. It's just because I'm telling you and you're memorizing it. So NO3 is a polyatomic anion. It's the nitrate anion. Remember, nitrite would be NO2, and they have the same charge. And it has and that charge is a -1. And the cation is potassium. And since potassium always forms a +1 cation, when they come together, it's a 1-to-1. Okay, but collectively, the NO3 -1 is an anion. You can't split that up. And we're going to call that potassium nitrate. All right, again, because you have to know and memorize the fact that it's nitrate. Now, you'll notice that I don't have potassium nitrate ion, okay, because ion means that there's an overall charge, which here there's not. the NO3's charge is balanced out by the potassium's charge. So you're going to drop the word ion completely. You can also use, so there's iron with 2 hydroxide groups, 2 OH groups. So iron is a variable charge metal. Let's say you don't even remember what the charges are possibly. But if you look at the anion that's attached to it, that's a hydroxide anion. You're going to have to remember that. You're also going to have to remember that that hydroxide polyatomic anion is carries a -1 charge. So if there are 2 of them and the compound is neutral, which it is, then there's going to be an overall, or there's going to be a -2 charge associated with the anion portion. So iron has to be +2. So because it's a variable charge metal, you have to write the +2 in Roman numeral within the parentheses right after iron. So it's iron 2 hydroxide. If the compound contains both a polyatomic cation and a polyatomic anion, we use the names of both. And that's pretty straightforward because there's only one polyatomic cation, and that is ammonium. So NH4NO3, you're going to have to be able to recognize that that's an NH4 plus and an NO3 minus, and when they come together, they cancel each other out. All right, so there are 3 situations that I have listed on this slide. The first one is just a known metal, known charge, right, a fixed charge metal, potassium, bound to a polyatomic anion nitrate, so you just say potassium nitrate. When you have variable charge metals, you're going to have to denote the charge in parentheses with Roman numerals, and you're just going to have to name the polyatomic anion. Hydroxide, you don't have a dihydroxide or anything like that, it's just hydroxide. And for polyatomics containing both a polyatomic anion and cation, you're going to have to say both. So this is just another example. Example is Na2CO3. All right, you know the cation, it's sodium. You don't have to put disodium or anything like that. We don't do that with metals. So there's no prefix in front of that, just sodium, and then you have to name the anion. And in this case, this one's carbonate. So sodium carbonate, and that's it. Again, you need to watch out for the variable charge metals though, because when you have variable charges, you have to show parentheses with Roman numerals. All right, so let's do some practice. So Mg and then parentheses ClO3. All right, this is a ionic compound, magnesium. It's not a variable charge metal, so we're fine. So it's just going to be magnesium. Then we have to name the polyatomic anion that's associated with it, ClO3. So it's chlorate. It's chlorate. I was just thinking ClO3, I was thinking chlorine and oxygen, and I was going to go from there, but it's ClO3, so it's chlorate. So magnesium chlorate. Next one, CuOH. First of all, that's a hydroxide group. Hydroxide carries a -1 charge. Copper is a variable charged metal. It's a 1-to-1, so it's copper 1 hydroxide. NaOH, fixed charged metal, so just sodium hydroxide. We have the NaHCO3. Okay, so this one, I didn't ask you necessarily to memorize the HCO3, but we have carbonate and we have this thing called bicarbonate. Bicarbonate is the one with the hydrogen on it. The one with no hydrogen is just called carbonate. And then sodium is a fixed charge metal, sodium bicarbonate. Here, potassium, and then MnO4, that's manganate. I'm sorry, potassium permanganate. I apologize. Permanganate. And that should make sense to you because looks like it's going to be more than 3, which it is, it's 4. Okay, so the next one, Ag2SO4. The SO4 is sulfate. It has a charge of 2-. Ag is silver. It's a variable charge metal, and there's 2 of them, so it has to be silver 1 sulfate. NH4NO3, ammonium nitrate. We have to name both of the polyatomic ions. If it was If it were NO2, it would be ammonium nitrite. Next one, NaClO. All right, well, first of all, it's sodium. It's not a variable charge metal. We don't have to do anything with the parentheses. So sodium, and then all we have to do is name that ClO. Now, if you remember, we'll go back up to the ClO3 really fast. Chlorate is ClO3, chlorite is ClO2, and if you remember, per means less than, and this sodium ClO, there's only one oxygen, so it has to be hypochlorite. Sodium hypochlorite. So again, you don't have to memorize. If you remember this, if you remember the chlorate, if you just commit that to memory, essentially, ClO3, and then you remember the rules of ite, and hypo and per, you're set. You're fine. Last one. All right, PbCO3, lead, variable charge metal. You don't even have to remember what are the possible charges. Just know that it's a variable charge metal. And then the polyatomic anion associated with it, that is carbonate. Right? It's not bicarbonate with a hydrogen, it's carbonate. Since it's carbonate, it's going to be a 2- charge, so lead must be a +2. We have to indicate it with Roman numerals, so lead 2 carbonate. All right, now we're going the opposite direction. We're going from names to formulas. This one's a little bit harder. You're going to have to remember the charges on all these. Aluminum sulfate. Aluminum is always a +3. Sulfate, SO4 2- is always a +2. So, if you have a +3, I'm sorry, it's always a -2. So if you have a +3 and a -2, you're going to have to find the lowest common denominator, which is 6. So you're going to have to multiply that aluminum by 2 and that sulfate by 3. Al subscript 2, parentheses, to indicate the sulfate group, close the parentheses, and then subscript 3 to indicate that there are 3 of them. Oh, I'm sorry. I was thinking about something else as I was talking. All right, so potassium chromate. I already gave you the answer. Okay, we'll just skip it. Kr2 because K2 because potassium carries a +1 charge, and chromate CrO4. So what would chromite be? Chromite would be CrO3. That carries a 2- charge, so you're going to have the parentheses on this CrO4 shouldn't be there, just to let you know. It's not incorrect, it's just not necessary. Potassium dichromate. So again, potassium is a +1. Dichromate carries the same charge as chromate. It's just a little bit different in its formula. Dichromate, 2 chromiums, so it's going to be Cr2, and then this is just straight memorization for you guys. There's a reason, but it's beyond the scope of this course. You're just going to have to know that the dichromate has 7 oxygens. Okay, so K2Cr2O7. Ammonium chloride. Ammonium is the only variable charge metal. Sorry, I'm getting tired. Ammonium is the only polyatomic cation. So NH4 plus, and chloride is a 1-, so it's a 1-to-1. Calcium phosphate. Calcium is +2, second column of the periodic table. Phosphate carries a 3- charge. So if we have a +2 and a -3 and we need it neutral, our common denominator is 6. So calcium must be multiplied by 2 and phosphate must be multiplied by 3. I'm sorry, calcium must be multiplied by 3 and phosphate must be multiplied by 2 in order to get to 6. So calcium, Ca subscript 3, parentheses, phosphate, anion, close parentheses, subscript 2 to indicate that there are 2 phosphate anions for 3 calciums. All right, and then calcium acetate. All right, acetate is one of those that I didn't necessarily ask you to memorize. Just know that it exists. It has a charge of -1. It's a hydrocarbon. And calcium, again, is a +2. So we're going to need 2. So the hydrocarbon with an oxygen, sorry. So we're going to need 2 of those to balance out 1 calcium.